Hey Earth Science! Today we're going to talk about the Coriolis Effect and how it can cause circular ocean currents, those gyres that we talked about in section 1. So I've got here an Earth, and the Coriolis Effect is best explained by showing rather than telling, because it's kind of a spatial thing anyway. You don't really get it if you just hear about it. You have to see it. So here we go. If we're going to put ourselves on the Earth, first thing we need to get is how the Earth rotates. So just to get an idea to visualize this, if we're here at home in Pennsylvania, because if we're anywhere right now, we're at home, where's the sun in the morning? Well, it rises in the east, which means you're here, you look eastward, the sun must be over here. You know what? Hold on. The sun. Okay, so the sun is over to the east. Okay? Where is it when it sets? It's in the west. Well, if you're here, looking west, looking at it over here. So this is evening, and this is morning. How does it get over there? Well, it has to pass overhead, doesn't it? Okay, so the sun starts in the east, passes overhead, and then it's over in the west. Okay, but we know the sun's not really moving. It has to be the Earth moving and the sun staying still. So how can I get the sun to start in the east and end on the west? Well, it's going to be like this. See, now it's directly overhead. Now it's to the west. Maybe you can't see that from your point of view. Looks great from here, though. All right, fine, I'll show you. So you see, in order for the sun to rise in the east and set in the west, the Earth needs to spin that way. So this is spinning eastward. It's one way you could look at it. You could also look at it as counterclockwise from the top. But spinning eastward, I think, will be fine. Okay, now I've got a question for you. After I pose this question to you, I want you to pause the video, think about it before you move on, because I want you to really put a little bit of mental sweat into this one. Does the Earth spin quickly or does it spin slowly? Anyway, pause the video, think about it, and then resume the video. I'll wait. Okay, that was a long time. Let's answer that. Does the Earth spin quickly or slowly? Yes. The answer is yes. So here's what I mean by that. If you're on the North Pole and the Earth's spinning, you're not moving at all. However, if you are on the equator and the Earth spins, you're moving very quickly, like many, many hundreds or thousands of miles per hour. I could have looked that up, but it's about 1,000 miles an hour. Okay, so you're moving about 1,000 miles an hour at the equator, about 0 miles an hour at the North Pole. Well, what about us? Well, we are here. So we are spinning somewhere between 1,000 miles an hour and 0. A couple hundred. Okay, so how does this cause the Coriolis effect? Okay, here's how. Let's just imagine for a second that the Earth is not spinning. It's standing still. We're going to start at the equator, and then we're going to travel northward to us. Yay. That was exciting. Okay, now let's make the Earth spin while I do that same thing. Okay, here goes. Okay. So far, not very exciting. But that last demonstration just created a problem that we need to try to solve. You see, the thing is, when the Earth is standing still, and I move upward, not a big deal. When I stop here, I'm stopped. But when the Earth is spinning and I'm standing still in the equator, I'm still moving 1,000 miles per hour east. Now, I don't know if you're aware of this, but if you want to stop moving east, you need to speed up in the westward direction. In other words, if you're moving east and you speed up northward, you're still moving east. In other words, this spinning Earth move north is a northeast path. And you start out moving 1,000 miles an hour east, and however fast you're going north. This eastward speed doesn't just disappear, which means by the time you get up to Pennsylvania, you're still moving 1,000 miles per hour to the east. But Pennsylvania isn't. So if Pennsylvania is only going like 700 miles an hour to the east, but you left a place in which you were moving 1,000 miles per hour to the east, that means by the time you get to Pennsylvania, you're 300 miles per hour faster than it. Okay, so clearly, this would be happening if, there wasn't any air to deal with, right? If the Earth really was as simple as this tiny inflatable ball, there's a lot more going into it, that you're not going to go 300 miles an hour just by walking north. There's a lot of friction involved that's going to wear you down. However, that kind of friction is not necessarily present in fluids like wind and water. So, here's what that means. If you have a current of water that's moving north, as it moves north, it will start to trail east. Not because it is picking up eastward speed, but because it always had eastward speed, and then it went up to a slower latitude. So I've got this inflatable ball because I can make some marks on it. So down here in the tropics, especially around the Caribbean, the water is very warm. I think that should be fairly obvious. Now, the course of the currents are determined by things like various temperatures in different places, wind patterns, and the continents. Well, it turns out that the wind has these same patterns. But let's get to the ocean, right? So we've got some ocean water down here in the Caribbean. It's very, very warm. And let's have it start to move northward. Down here at the, there it is, at the equator. So down here in the tropics, this water moving northward, it starts out with a great eastward velocity, and it ends up at a place where the eastward velocity is slower, which means it continues at its own eastward velocity while the rest of the world can't keep up with it. And so it starts to trail over. It has a constant northward velocity and a constant eastward velocity. The reason that this path looks curved is because it's going through slower and slower parts of the Earth. Remember, this straight line has to take into account that it is on a moving surface. Okay, so that's going to trail up. So this is water from the Caribbean. It's tropical water, which means it should be fairly warm. This is one of the reasons why up at these latitudes, like the Jersey Shore Cape, what cape is that? I can't remember now. The Jersey Shore is like a really nice beach. The water's really warm. Ocean City, Maryland, if you've ever been there, it's really great. It's because it's got these warm tropical waters that have only had to travel 2,000 miles. So they're still fairly warm. But once we get up to the North Atlantic Ocean, this water's heat is starting to wear out. But it's worth noting, England has the same latitude as British Columbia, but their climates are very different. There's a lot more warm water here than there is over there because of this. But by the time it gets up here, let's just say the heat's gone. It's up in the near the Arctic. It can't stay warm forever. So it runs into the continent and starts to come down. Now remember also, it has undergone some friction, so it's also slowed down. Let's say it's down to only a couple hundred miles per hour eastward now, remember, in the spin. As it moves southward into places that are spinning faster and it can't keep up with them, it will start to fall behind. Then the cycle is complete. So this gyre has a fairly calm spot in the center. Remember, that's called the Sargasso Sea. And this kind of pattern is going to be in the northern hemisphere over here as well. So let's just get the red marker out again. Repeat this little exercise. So we've got a much larger ocean here, the Pacific Ocean. Warm tropical water. It's going to be moving up here. Same path for the same reason, that this water is moving very quickly eastward, but then it moves up to places that are not moving quickly eastward, and so it passes it. As it gets up into Siberia and Alaska, it cools down. As it spends so much time up here with friction, it slows down, and it starts flowing back down. Now, the Pacific Ocean is huge. I'm just going to draw this part of it. But this is one of the reasons why California beaches are cooler than East Coast beaches. It's because the waters around them are these Arctic waters coming down from Alaska and Canada. Now, obviously, once you get down to Southern California and to Mexico, you're back into tropical waters. But around Oregon, Northern California, the beaches are not warm tropical beaches like you have at the same latitude on the East Coast in North Carolina. Those are the same latitude, but the waters over in North Carolina are warmer than they are in California.